In this lesson, we're going to talk about inverses of exponential functions. We know that the graph of an exponential function looks a little bit like this with an asymptote, okay, generalization. So what we do to find the inverse of this would be to switch the x and the y. And by doing that, and if we want to try to get the y by itself, as we learned in section 9, is that we would change this to a logarithm, where it becomes log base b of x equals y. And that would get the function by itself, and that would be the inverse function. So let's kind of take a look at what that looks like. So if we just take the regular function to the x power, we plug in -2 for x, that's going to give us 2 to the -2, which we know is 1 over 2 to the second, which is 1/4. When we go to plug in -1, we plug it into the x value, which is 2 to the -1st, which would be 1 over 2, which is 1/2. If I plug in 0, that's 1, then 2, and then 4. Now, a couple of things. I could make a t-chart of the function and start plugging it in. So what we could do is if I thought about plugging in just random numbers, if I plug in 2, let's say 3 for x, this doesn't really make much sense. If you plugged in your calculator, you get a kind of a weird decimal. But if we think about it this way, if I took and put a number in for the y value right here, let's say 2, and I change this into an exponent, now plugging in here, it actually gives us a value, which would be x equals 4. So, and I fill in the y values to get the x. Now, if you take a look at this, 4, 2, I'm actually going to move it down here, 4, 2, they're inverses. So we switch the x and the y. So I technically don't have to do this for every single problem. I can just switch the x and the y because that's the definition of an inverse. 1/4, -2. 1/2, -1. 1, 0, 2, 1. Now, if I go and I start kind of making my graph and start putting the points, -2, 1, -4 is there, -1, -1/2. We talked about that anchor point being 0, 1, and then 1, 2, and then 2, 4. We can kind of see that shape right there happening. When I go to do the inverse, I start plotting these points. I get 1/4, -2. I get 1/2, -1, and then 0, 1, and then 2, 1, and then 4, 2, which looks like that. And as we talked about before, y equals x is right here. And we can see that those distances between it are the same because inverse functions have equal distance. So again, we talked about this before. A logarithm is an exponent is a logarithm. And so then if I switch the x and the y, I can see kind of how the shape of those graphs are very similar, just reflected. So if we go to graph number 2, one of the things that we're going to kind of look at first is if we change it to an exponent. So let's take this, change it to an exponent, and it becomes 2 to the y power equals x. Now, again, we kind of already did this up at this point, correct? But again, what would happen if we were starting from scratch is that we would start filling in the y values because that y value is here. So we'd put in -2, -1, 0, 1, 2, and I'd plug them in. So this would be 1/4, 1/2, 1, 2, and then 4. Ran out a little bit of room. So when I go to put that in, it looks like this. So I'm just plotting these points and seeing what happens. And it kind of swoops like this. And a couple of things. You can see as we're going this way on the graph, 1/2, 1/4, it's getting closer and closer to that 0, but it won't touch. So what happens here is there's this asymptote. And if we can start filling in some of these things, the domain of this, we've talked about this before, okay, because it won't pass that asymptote, will have a domain of 0 to infinity. And that range, okay, all the way down, so negative infinity. And technically, even though it's slowing down with how far it goes up, it would continue to go on forever. So it does go on for infinity. Now, what happens to these limits? Well, let's take a look as x approaches infinity. So as it's going this way, what's happening to the y value? Well, what's happening to the y value is it is going to increase. So as it's going right, the limit as x approaches infinity is infinity. And again, looking the other way, this one, as x approaches 0 from the right side, so again, looking at the graph, going this way to the left, as it gets to 0 right here, what's happening to the y values? Well, you can see those y values are going down, and they go down forever, so to negative infinity. And again, because that's approaching, there is a asymptote. It's a vertical asymptote, so it's x, and it's x equals 0. One of the things that we should notice and make sure we kind of note right here is that the intercept right here is 1, 0. That's kind of like the anchor point that we were talking about before with exponential function. It will always start there, or it kind of go through that intercept. It's not a y-intercept this time, but an x-intercept. And if we look at that concavity of how this is approaching, you can kind of see, kind of has that almost, or that start of that frown. So it's that upside down frown, so it's concave down. So again, kind of circling back to some things that we talked about before. If you have, let's say, an exponential function, remember that anchor points at 0, 1. We have that asymptote at y equals 0, and it starts low from the side and it goes up. And one of those things that right here is whatever that base is. So if you had like 3 to the x power, that point's going to be 3. Whereas 5 to the x power, it would be at 5. And then when we have the logarithm, again, there's that reflection line. So what's going to happen is it just kind of flips around. Instead of a horizontal asymptote, it's a vertical asymptote. Instead of that anchor point being at 0, 1, that anchor point's now going to be at 1, 0. And again, it's going to flatten and then swoop up like that. So let's quickly kind of look at this and talk about some patterns that we've seen with this versus some other things that we have. So if I'm going to change this to an exponential, it would be 1/2 raised to the y power equals x. Now think about what that half means. It means 2 to the first, okay, so 1 over 2 to the first, and so that would become 2 to the negative first to the y, which equals x, which would be 2 to the negative y power equals x. So if we made just a very quick t-chart, and again, remember we're going to fill in the y values, -2, -1, 0, 1, and 2. If I put -2 in here, so opposite of -2 is 2, So that's going to become 4. This is going to become 2. 2 to the 0 power is 1. Then this is 1/2. And then this is 1/4. Sorry that I'm running into the text. And we start plotting it. So 4, -2, 2, -1, 1, 0, 1/2, 1, 1/4, 2. And I want you to think about that shape. Still kind of the basic shape of a logarithm, right? We see the asymptote happening here. That's nothing that changed. See that anchor point? It's still going to be at 1, 0. But compare this to this one. Do we see the reflection right here? The reflection happened over the x-axis. And that reflection happened over the x-axis because we're switching the y values. And because of that, again, that reflection is going to happen on the x. So a lot of these translations that we've seen before are going to happen with these logarithms as well. So domain. Domain is still 0 to infinity. Range is going to be -infinity to infinity because this goes down forever. And this is going up forever. As x approaches infinity for the limit, so as it's going this way, what's happening to the y values? Well, those y values are going down towards -infinity. Look what's happening now to these y values as it's approaching 0 from the right side. What's happening to the y values? They're going up. So it's going to be infinity. Our asymptote is a vertical line, x equals 0. We talked about this already. That intercept doesn't change. It's still at 0, 1. But look at that concavity now. Okay, so here's the graph. See kind of that start of that smile? So it's going to be concave up. In example number 4, we have the situation where it asks you to suppose that you're going to invest $2,500 in an account that pays an annual interest rate of 6% compounded continuously. We know that the balance in the account after 2 years can be found by the model A of t equals 2,500 e to the 0.06t. So this right here, it looks like it's exponential, but because of the way those numbers are in the exponent, technically it could be written logarithmic, and you'll see this by the graph. So what it's asking us to do is just to kind of fill in the graph and kind of see what that pattern actually looks like. So if I plug in 0, e to the 0 power is 1 times 2,500, that's going to be 2,500. If I take 4, I plug it in for t, you're going to get 3,178 and 12 cents. If I plug in 8, we're going to get 4,040. Pause the video real quick and plug in 12 and 15.